Very good evening, everybody. So, how is everyone doing?
Good, sir.
Good.
Yes, sir.
Okay. Okay. What about others? How are you all doing? All fine? Okay. Great. So, every day we are learning some really great concepts of physics. Many concepts we have already done. Last time we discussed a really interesting concept of relative velocity, which actually also has to do with relativity, as what I said. So today also in the same series, we are bringing up new concept, and that new concept will be Newton's laws of motion. Now, let me tell you, it will not be the same Newton laws of motion as you learned in your ninth. I mean, obviously the laws will be same. I can't change the laws for 11th grade. But the fact is, we will be learning in much more detail. It won't be just a theoretical chapter where we will state three laws and we'll move ahead. No, here there'll be many application of the laws. So you will see, based on the same few laws which you learned in your ninth, so many immense applications can be done. We can involve multiple systems where thinking about forces will be so difficult. There'll be multiple ropes connected on a pulley, blocks will be hanging, they will be having inclined planes where blocks will be sliding down. uh, Sometime even the inclined plane would be moving. So there'll be a very complex system, combination of inclined plane with the pulley, with the ropes, with friction, everything will come up. And that makes the application really complicated compared to what you have learned in ninth. So here you would have to give great effort what you have done in your ninth on this chapter. Now it will be 1,000 times more. And let me honestly tell you guys that the moment after 10th this 11th portion start, initial few chapters students are able to do. Also they face difficulty in calculus, but somehow after a little here and there one is able to do those chapters. But the moment the chapter of Newton's laws of motion starts, now students start facing the difficulty. So this is the biggest obstacle that anybody face who shifts from 10th to 11th. The biggest obstacle arrives in the form of Newton's laws of motion. And I've seen from past years, a student, starting to give up after this chapter. They're like, suddenly this chapter is as such, we don't know, we feel, flabbergasted, we don't know what to do. But if done in a very proper way, then this chapter can also be understood very properly. So today you will going to see that. So yes, I can see many people on YouTube have joined. So all the people on YouTube, very good evening to you all. I can see Krim, I can see Saj, Jayesh is there, Abdul is there, all of you are there. So very good evening. So let's begin, guys. What is this chapter all about? I'll share my screen and let's begin discussing on it. So first of all, I would like you all to recall the three laws of Newton that you guys have learned. So please revise it for yourself, what those laws actually stated, if you remember from your ninth grade. And then we will see application of those in today's class. So do you guys remember the three laws? What was the first law? Yeah, so many people are responding on the chat that the law was nothing but the law of inertia. Yes, you're absolutely right. First law was essentially the law that even Galileo gave. Okay, so all these discussions were started by Galileo, Copernicus, Galileo. These were the initial physicists who started talking about it. And then later on, the Newton, later on Newton joined the bandwagon, and he also gave many new, you know, facets to the same law. So this law is very simple. If I talk about Newton's first law, let's talk about the first law. So first law talks about inertia, and inertia is a property we all feel. One can feel inertia. You, all, me, everybody, we feel the inertia. Inertia simply means revolting against any change. So what it means, we don't like change. We don't want to have change. And that happens in day-to-day life. If we are learning from some teacher, we never like to have a change if the teacher is teaching in a good way. Obviously, if it is not, then you would definitely want it. But if let's say we have got a good teacher, we would like to continue there. That's a change we won't want. We don't want. We don't like to change. Our home. We have memories with that. If we are sleeping, we don't want to get up in the morning. We have an inertia towards waking up. And also in the night, when parents are telling us to go and sleep, we have a revolt of not sleeping. We want to watch one more episode of some web series. We want to play more and more of the games. So it is like that we want to just oppose everything. We just hate change. That's all we do. That's exactly inertia. Not only us, we also have objects doing that with us. Around us, every object does the same. In what way it does that, we're going to see. So Dhanush is saying when we dust a carpet, the dust falls down, which is an example of inertia. Yeah, there are many applications of inertia. Even the applications or the examples I gave to you right now, they are also inertia. Inertia is not only in terms of the physics inertia, even in our human habits, that's also an inertia. Just the tendency to oppose. Now, when it comes to objects being there, so what is objects inertia? Objects inertia are defined to be in three ways. If let's say an object is at rest, it would like to be at rest. Think about anything that is around you. It is not moving. There is a box, there's bed, there's table. They're not moving. They are at rest. They don't move. They won't move unless you apply a force. You try to push them. All right. So they won't move unless you apply any force, unless your house is not haunted. If that's the case, they would move even then. So in normal scenario, objects don't move without applying the force. So inertia of the rest means something at rest would like to be at rest. And then we have inertia of motion. Something that is moving would like to continue the motion. It doesn't want to stop. If you want to stop, you have to apply brakes, like in the car. So car is moving. Now let's try to see the inertia of rest and motion in a single picture. You are inside your car. Okay. Right now you're sitting. Car is at rest. Somebody suddenly accelerates the car. So what happens? We suddenly fall back because of the huge acceleration that is produced in the car. So what is the reason that we suddenly fall back? Because what happened? The engine made that metallic car to suddenly move forward, but your bodies are not connected to it. Your only lower body is connected. You're sitting on the seat of the car, not your upper portion. Your upper portion may be like this. You're sitting like this, isn't it? So your upper body is not connected to the car. Only the lower body is. So along with the car, your lower body moves forward along with the seat. But what about your upper body? It tries to remain where it was. So it's not that you fall back. It's even wrong to say that you fall back. What has only happened is you are at your place, but your lower body has moved forward. Isn't it? If your lower body will move forward, what would you feel? As if somebody has pulled your legs. So you will just fall back, isn't it? So why your upper body did not move? Because it was in the condition of rest. So until unless no force acts on it, it will try to remain there. When only it starts to move. It only starts to move when it hits the back of the seat. When your body hits the seat, then suddenly you start to go with the car, because now that seat is applying force on you. All right. So that's the inertia of rest. Now, similarly, suppose the car is moving at high speed. So it is right now moving at high speed. You are sitting like this, and suddenly the car applies brake. The driver applies brake. Right now, your upper body and lower body both were moving. They were in motion. Right. And suddenly now the brakes are applied, because of which the car stops. So what will happen? Your lower portion will immediately stop because it's connected to the seat. But what about your upper body? Upper body still wants to move forward, right? So again, the same thing has happened. You have not moved ahead. It's just that your lower portion stopped moving and upper portion keeps on moving. And that's why you tend to fall ahead, right? Our lower body just remains there and upper body continues to move because it had an inertia of motion, isn't it? That's why we fall ahead. So that's the inertia of motion. Now, in the same car, we can also see the third type of inertia, which is of direction. In that, whenever the car takes a turn, you must have seen it. So suppose if let's say car was going in the right direction and suddenly it takes a turn like this. Where do we fall while taking the turn? We fall in this side, isn't it? That's where we're going to fall if our car took a turn like this. Why we fall in that direction only? Because that is where the car was supposed to go. In that direction, the car was moving, isn't it? And so your body would like to maintain the motion in that direction. So that's why it falls there. Car has changed the direction, but your body wants to maintain that direction which was initially there. So you fall on that side. So that means your body would like to maintain the direction. Reluctancy to change the direction. Okay, that's inertia. Then after inertia, which is the first law, Newton actually said the same thing in other words. He just changed the words. What he said, that an object which is at rest continues to remain at rest. An object which is moving continues to move until and unless acted upon by a force. So he just said the same thing, that something at rest will remain at rest, something in motion will remain at motion until unless you don't apply force. Applying force, you can change it. Any moving object can be stopped by applying force. A stationary object can be made to move by applying the force. So he just changed the language, and that's the first law. What was the second law? Then he talked about what is the relation between this force and its effect. So there is a force and there is an effect of the force on the object. So what is the effect of a force on an object? The effect is change in momentum. Force actually causes change in momentum. Now, do you guys understand what is momentum? That also you must have learned. Momentum is represented by P and it is mv, mass times velocity. If you put it as a vector, it will be like this. P vector equal mv vector. And what Newton says is that force causes a change in momentum. All right. Acceleration is secondary thing, Siddharth. That was not the Newton's second law. People think F equals ma is Newton's second law. That's wrong. It's the fallacy. The actual Newton's second law had to do with force and momentum. Now later we can arrive on that equation using this. So now what Newton said? Newton said that if you want to change the momentum, you can change it by applying a small force, and you can change it by applying a huge force also. How is that so? Take for example, a box is at rest. Or let's say a ball is there, a tennis ball is there, and you're moving it very slowly on the floor. You're just rolling it. So slowly, its speed is increasing. Now you continue to apply the force. Let's say you're on a large ground, a plane is there. You keep on applying the force and speed will keep on increasing. Finally, it will attain a very high speed if you continue to apply force. How much high speed? That high as if it has been hit by a batsman. So fast it will start to go. Maybe let's say with 200 kilometers per hour starts to go. So difficult for a person to do it. But let us say that this much he was able to provide. Now, obviously you can understand, in order to give such high speed, he would have to roll it for a very long time. He would have to keep on rolling it for a large distance to provide the speed all the way starting from rest. But what do you realize? The same thing can be done by a batsman in a second. He doesn't even need time to do this. What he needs to do? Just throw the ball and hit with the bat. And what will happen? The moment it will hit the bat, it'll start flying off with such huge speed because of the whack. The batsman just hits it. So what is the difference between the two scenarios? In both cases, ball speed changed from 0 to 200. Here also 0 to 200, here also 0 to 200. So can you guys tell me what was the difference here? Time taken, exactly. In the second case, this change happened all of a sudden. And in the first case, this change took a lot of time. He almost kept on rolling it for many minutes. And then only he was able to do it. So what Newton said, the difference between the two is, in the first case, he's applying a very small force. And in the second case, he's applying a very large force. And so what Newton said, that if time is larger in changing the momentum, force is less. And if time is less in changing the momentum, then force is more. The other way to put it up is force is rate of change of momentum, delta P by delta T. What delta represents? Change. Now, delta is a big change. I hope all of you have learned calculus now, which talks about instantaneous change, a very small change. And that small change is represented by dP by dt. And what do we call it? We call it rate of change of momentum. That's calculus. That's actually the Newton's second law. So Newton's second law states that force is equal to rate of change of momentum. Actually, he said proportionality, but constant we can assume as 1. But you will say, sir, we know the second law as F equals ma. How do we arrive at that? So let us substitute the value of P here. P is nothing but mv, mass times velocity. And now you can just apply the product rule of the differentiation. First keeping the mass constant, differentiating the velocity, then keeping the velocity constant, and differentiating the mass. What this implies? The first portion says dv by dt. What is rate of change of velocity with time? That's acceleration. So first term is ma. What about the second term? That's rate of change of mass of the object. This is the actual equation. Now what happens is, in most of the cases around us, the mass is not changing on applying force. Do you think if you start pushing a table, its mass would change from 60 kgs to 50 kg? No, it'll remain constant, right? So in most of the cases, this dm by dt is 0, because dm by dt means rate of change of mass, how fast the mass is changing for the object. So for general studies, in general scenario, in general, dm by dt is 0. And that's why the law reduces to F equals ma. So F equals ma is only a special condition, not the actual law. Actual law is this. Yes, Amit, I'll explain. Now, is there any case really where mass could change? Because we always say mass is conserved. How can it even change? So can you think of a case where mass is changing for an object as it is moving? So anyone? Mass of object changing as it is moving. Can you guys think of a case? People on YouTube also. Can you guys answer? A case where mass is also changing. object disintegrates due to friction. That can be a case, Cavalya. Radioactive material. No, radioactive material, there isn't much of mass change, which can cause change in acceleration. That's very less. It's usually in few grams. Asteroids, yes, because they, you know, leak out matter as they are moving. The best example you all could have given is a rocket. As a rocket flies off, it goes into its orbit. What happens then? It has a huge amount of fuel stored in it, isn't it? So rocket has a huge fuel stored in it. And as the rocket is propelling upward, it's burning all that fuel. And so as rocket propels, its mass keeps on decreasing. All right. Snehal, yes, ice is there, but it has to move first of all, Snehal. We're talking about moving objects which are losing the mass. Car, why does car loses that? But that is negligible, Jay and Jainil, because if let's say the car is weighing so much, let's say it's thousands of kgs, that's what the car weighs, and how much weight the petrol would going to have? Hardly 1 kg, 2 kg and all. So changes are very negligible. But when we talk about a rocket, rockets, if you would see, the important parts like satellites and all are stored in the upper part, which is hardly 10% of the entire rocket. The remaining 90% is all the fuel. So in rocket's case, fuel occupies a large volume of the rocket. That's why the change is immense. In regular car and aeroplane, it is there, but very negligible. Okay. Something that can be neglected. So guess what? For rockets, we cannot apply F equals ma. So when you think of scientists sitting in ISRO and NASA, they don't apply F equals ma equation. They know it's wrong for them. They actually apply this equation, the actual Newton's second law. Is it clear to everyone? So for rocket science, we use this. All right, now Samiksha was asking about this differentiation. So Samiksha, you learned about differentiation yet? Product rule and all? Okay, so that we will be doing in regular classes. So even the people on YouTube, I'll tell it to them that since we are just discussing few topics only here, the actual class in order will going to happen from 10th May in the regular class. So there we will be starting with calculus and vectors. There I'll explain you how these differentiation parts are done. All right. So wait for the regular class on 10th. So right now you can see I am picking up topic from various chapters. I took kinematics 1, kinematics 2, then we went with relative velocity. Then today we are discussing force. Next class we'll be discussing friction. These are all various chapters. So yes, all we are learning we'll be doing in order again. This is not the actual way of learning. Guess what? Newton's laws of motion will come only after a month or so. For an entire month, we will be learning calculus, vectors, units and dimension, kinematics 1, kinematics 2, 1.5 months later, it will come. So wait for the regular classes on 10th May. Okay. I'll explain all these things again. Okay. So for time being, we just have F equals ma equation for us. Because in most of the cases we see dm by dt is 0. Fine. All right, now F equals ma, what kind of question we can expect? It is not any longer a 9th grade. where you will just have a mass given as 2 kilogram, force given as 2 Newton, and they will ask you acceleration, then just forget about it. That's not what will going to happen in 11th. Here, vectors will be coming up. Vectors will be involved in force, and many other things will be involved. So, do you guys know about vector components? How to take components of vector? No, right? Okay. So that also, as I said, for the very first month, we will be doing these things. The entire 1 month of May, when our classes start on 10th May, we will devote it for learning vectors and all. So for the time being, at least, I'll just give you a short idea. Yes, Samiksha, IJK are unit vectors. Components are a little different. So right now I'm giving you a pretty vague idea, guys. Later we'll do in detail. A vague idea could be like this. Suppose I tell you that this is the coordinate axis. And suppose I have a line. This line actually represents a vector, an arrow. All vectors are arrow basically. It may be like force is acting like this. Okay. So a vector is there. Let's call it vector A. And suppose it's making theta angle with the x-axis. And this is our y-axis. Now, if I tell you that I shine a torch from the top, I just shine a torch on this vector from the top. What kind of shadow you will going to see on the x-axis? You're going to see a shadow like this. In this way. That's the shadow you will see. That's called the component of A along x-axis. And can you guys tell me what would be the length of this shadow? If the length of the original arrow is A, how much would be the length of this component? So I guess all of you know trigonometry, right? So in trigonometry, if we apply in this triangle, and I say that the base of the triangle is x, then which trigonometric function I can apply over here? Anyone? Cos theta. Shreya is correct. Because this is the base and this is the hypotenuse. Cos theta is something we should apply here. We should say that cos theta is x by a, base by hypotenuse. Everybody clear with this? So base by hypotenuse is this. So we get the value of x. X is a cos theta. That's the shadow along x-axis. Or we call it as the x component of a. And similarly, I can shine a torch from the right side. And then I can see the shadow. You will see a shadow of this length. What is the length of this shadow? It is same as this. If we get this length y, that is the same as the shadow. Now in this triangle, what should I do to get y? Sine theta, isn't it? I should apply sine theta law, and that will tell me perpendicular by hypotenuse, y by a. And that will give me y as a sine theta. Correct? So I got both the components. I got the x shadow, got the y shadow. Now, right now, this arrow had no meaning. It was just a general arrow. But now in our chapter, this arrow will imply a force and we'll be taking components of force. Force along x-axis, force along y. And that will be so useful, we will realize. Okay, so shall we move ahead? Everybody can now understand this. Length of the shadows, A cos theta, A sin theta. This will be used everywhere, guys, in physics. So let's see the use of this. Now suppose that if problems were so easy, then life would have been so easy. But unfortunately, it isn't. If they would have given us a force and the mass, we could have determined acceleration so easily as A equals F by M. Here the answer would have been 1. But this is not 9th grade. This is 11th grade. Nobody will give you a question like that. So easy. If at all they would have to give a question like that, the simplest possible question you can ask them will be when the force is acting at an angle. Like whenever we go to a shopping mall, then we have a cart, or any grocery store you go. So if this is the trolley, for the timing, I'll not draw the wheels because having wheels will cause some other effect called rotational mechanics. I want to discuss that right now. Let's keep it simple. That is just a trolley which is dragged. All right. So you must have realized we never apply a force horizontally. The handles are like this. So our force most of the time is like at an angle. Maybe like this. So like this is my force. And this is 2 kilogram. And they may tell us that this force is 60 newtons. Determine the acceleration. So now can you do the same? Acceleration will be 60 by 2, 30. No, absolutely wrong. Answer won't be 30 here. Why? Because will the block be moving in this direction? Will that trolley be moving into the ground? No, it'll be moving flat on the horizontal floor. Its motion will be along this direction. So that means I'm only interested in the part of force that moves it horizontally. I'm not interested in the overall force. Now, what do you mean by the part of the force? This, just like we took two parts of A, one was X, other was Y. That's why they are called components of A. This is the X component of A, this is the Y component of A. So how about I split this force into two parts, one horizontal and one vertical, like this. And suppose they tell us it's acting at 60 degrees. So what will be our component along x-axis? Can you see what was the component along x-axis? A cos theta. So here it will be F cos 60, because instead of A, I have F, force. So F cos 60 is the force. And now this F cos 60 is responsible for this acceleration. So we must use that. I must write F cos 60 equals ma, not the entire F. And what is cos 60? F by 2, 1 by 2. F is 60. So what is our acceleration coming? 30 by 2, which is 15. Our acceleration would just be 15. So this is how now questions will be very different from whatever you have learned in your 9th grade. Yes, acceleration is a vector. So is force, Shivank. Force is also a vector. So everybody can write down, and then we may try one or two problems like this. So suppose there is a block. Now the same trolley maybe. This time instead of pushing it, you're pulling it. So this is how you're applying the force, F. And you're applying at an angle of 45 degrees. The mass is 2 kilograms. And you provided it an acceleration of √2 meters per second square. So what is the question? When you applied this force F, acceleration was √2 meter per second square. So you have to determine how much force you must have applied for this to happen. Yes, Sambhav, you're right. Yes, Shreya. Yes, Shivank, correct. No, Dhanush, it's wrong. Samiksha, it's wrong. Jayesh and Akhil are correct. Shambhavi is correct. Okay, so let's see how we could do this. Yes, Samiksha, now you're right. So again, we'll take the components, right? This F will have two components, one horizontal, other is vertical. I'm not interested in vertical. I'm interested in horizontal. So what will be the horizontal component? F cos 45. And that is causing an acceleration of √2. So F equals ma. F cos 45 is equal to ma. Mass is 2, acceleration is √2. Now cos 45 is 1 by √2. That's equal to 2 √2. You cross multiply √2 and that will be 4 newtons. So see, now things have changed from what we did last time. Okay, let's try something really interesting. Have you ever wondered that whenever you keep any object on an inclined surface, suddenly it starts to move? And all of you must have seen it. Let me show you that. So here I have a white color object, as all of you can see. Maybe I'll unshare my screen so that you're all able to see very properly. So you can pin my video and see. So here I have a white colored object, and that I'm keeping on this horizontal platform. Now what I'll be doing is, I think now it must be visible to you all. Now what I'll do is I'll gradually tilt this platform. So initially you don't see anything happening, but when I tilt more and more, then suddenly something will happen. Like this. It started to move. Did you all notice this? Suddenly it goes in downward direction. Have you ever thought why it moves in downward direction like that? Gravity causes that, right? What stops it initially from moving? Friction. After a while, friction stops moving it. Initially, it stops, but later gravity overpowers. But it can't just be gravity, because gravitational force never changes, right? Do you think that as I'm tilting this platform, gravitational force is increasing? No, right? Gravitational force is always constant. It's mg, mass times the gravitational acceleration. So why it is like that, that initially the force is low, only when I tilt it more and more, then the force increases. Incline increases, but what effect incline causes? Because gravitational force isn't changing. So what is incline doing? What is that increment in inclination is doing? Have you guys thought about it? But initially there was surface for the object to rest. Surface is there finally as well, Dhanush. It doesn't come out from the surface. It slides on the surface only. It reduces the normal force. So friction reduces. That it definitely does. But the fact is, not only friction reduces, there is something else that happens. See, guys, you're not getting into the point. You all are saying correct things, that yes, incline is increasing, slope is increasing, and slope suddenly overpowers the friction. But I'm saying in terms of force, what is increasing? There must be a force that is increasing constantly as I am increasing the inclination. What is that force which is increasing? It can't be just gravitational force, because gravitational force is constant. No, I haven't. No, acceleration is not force, Dhanush. I'm saying there is a force which is increasing as I increase the slope. It can't just be gravity. There has to be something else as well. Yes, so we can say that it's not just gravity that is there. We have to actually see the effect of gravity down the incline. And that must depend upon angle. And does it really happen? Well, let's try. Suppose this is an inclined plane. And you have kept your block on it like this. Its mass is m. The angle is theta. Now I told you gravity never changes. Whether it's a tiny slope, whether it is a big slope, gravity is just gravity. It just acts downward. Even if the slope is very low, the gravity would still act downward only. If you increase the slope too much, then also gravity acts downward only. Its value is also fixed. So are you guys understanding? Gravity is not affected by what you are doing, what your incline is. It's always same on that object. But there is something changing, and let's try to see. We see here, gravity is not in the direction of motion of the block. Can you see? Gravity is downward. While if the block is moving, in which direction it moves? It moves down the incline in this direction. That is where its acceleration is. So that means the entire mg we are not interested in. There is only a component of mg that moves it down. Isn't it? Only a component. So we would have to take components of mg also. So should I take components here? Let's do it. One component down the incline like this. One component perpendicular to incline like this. And we want to know their values, which one is cos, which one is sine. How do we determine that? First of all, we would have to see where the angle is, because we saw that whichever one is with the angle, that's the cos, that's the x component, whichever is with the angle. Now here, where is theta? We want to know that. Let me just reshare the screen. It's not appearing. Okay, it's still not appearing. Something has gone wrong. Okay, finally it appeared. Let me reshare. Okay, so we can see that this is mg, this is theta, and this is 90 degrees. So how much this angle should be? Isn't that a right angle triangle that you see there? If this is theta, this is 90, then shouldn't this be 90 minus theta? Shouldn't that be 90 minus theta? And if this total is 90, then this should be theta. Correct? And so the component we were looking for that should be cos is this one, because it is with theta. So we got that this is mg cos theta, while the one responsible to move it down is mg sine theta. Mg sine theta is responsible to move it down, isn't it? So which force should I consider here? Just the mg sine theta. And that is providing the ma down the incline. So m cancel. And what do we see? Acceleration down the incline is g sine theta. Obviously, I have not considered friction yet. I'm keeping it very simple. There isn't any friction for the time being. It's just a smooth floor. Now we will understand the reason why, as I was increasing the slope, the block got more tendency to move down. Now we can understand that. Can you all explain why is that? Increasing the slope increase the tendency to move down. Yes, because the force that is sliding it, mg sine theta, in that the theta is increasing. And as theta is increasing, the force that is moving it down is also growing, isn't it? And when you make it horizontal, when theta is 0, that force is also 0. So in horizontal surface, block don't move. They only move when you create certain angle. At 30 degree, it will be mg by 2. At 60 degree, it will be root 3 mg by 2. And at 90 degree, it will be mg again, because 90 degree means you have made it vertical. Block is just freely falling. So that's the fun of vectors and its components and making the blocks move down the incline. These things become fun. So I hope all of you are clear with this. Why not try a question? Suppose I have a triangle in the sense of wedge, and there is no friction anywhere for the time being. And I have kept a block at the top over here. The inclination angle is 30 degrees. I just release this block. All right. Now this height that is there is given to us as 20 meters. Oh, wait, 10 meters, not 20. Oh, wait, I want to give some values which are good for you. So let me think on it. 5 meters only, as a matter of fact. The height is just 5 meters of this wedge. And from that, the block is released. So what will happen? Block will slide down the incline, isn't it? Let's say we released it at time 0. When we release, we started our stopwatch. A stopwatch started ticking. Now we will keep on noticing the time till it finally reaches the base. So you guys have to tell me what time our stopwatch will be showing when the block reaches the bottom. Question is clear? Release from the top. We started measuring the time. How much time it will take for block to reach the bottom of the incline. Mass of the block is not given, Sambhav. Maybe because you don't need it. You just see, try to solve. No, Sambhav, there is nothing as maybe. You have to give the exact answer. There is a proper calculation for it. Sorry, not Sambhav, it's Shambhavi. I'm sorry. So Shambhavi, calculate it properly. Okay, I think Siddharth's answer is correct. Let me do the mind calculation also. Yes, Siddharth, your answer is correct. All the people on YouTube, what's your answer? Yes, even Shreya got correct. Samiksha is correct. Kishore is correct. No, Sambhav, that's not correct. Yes, guys. So what's the answer? So this question has to be done using equations of motion because it's an accelerated motion, right? And in accelerated motion, we first need the acceleration of the block. So down the incline, how much acceleration will it have? Well, that will be g sine theta. Taking gravity to be 10, sine of 30 degrees. What is sine of 30? Half. So the acceleration of the block is 5 meters per second square. It goes down with an acceleration lesser than gravity, 5. Now, how much displacement will it cover? So displacement, which is the length of the hypotenuse, it'll cover from A to B. That is a displacement it'll cover. And what is the length of AB? The length of AB, you would have to apply the sine theta. And that sine, if you will apply perpendicular by hypotenuse, you will get the hypotenuse as 10 meters. So it has to cover a displacement of 10 meters, isn't it? Now, so we have the displacement with us, S equals 10, U is 0 because it is released, acceleration is 5, and we need the time. So the only equation to be used is the second equation of motion, S equal ut plus half. So S is 10, U is 0, half A times t squared. This quite clearly gives us t as 2 seconds. Can we use speed formula? Which speed formula, Dhanush? Speed equal distance upon time. No, because that formula is valid only when it's only valid when uniform motion. Uniform motion means when speed is not changing. Here, block speed is changing. If think about it, you could use that formula. Then which speed will you substitute? Will you substitute the initial speed, which is 0? Or will you substitute a speed which is in between or at the end? So that formula can't be used because speed is not constant. So that's the way to solve the questions on Newton's laws of motion. Now, there are many other problems apart from this that we will be doing, like the questions involving a pulley and rope. So what thing happens if there is a pulley and we put up a rope on it? Now, what kind of force a rope applies? Can you push objects with rope? No, right? You can only pull the objects with the rope. So rope always applies a pulling force. And that pulling force which exists between any kind of rod or a string or any kind of thread, all these forces, pulling forces, are named as tension. They're all tension forces because they're used to pull any object. So if there's a block, you can only pull it with the help of a rope. This is the rope. So you apply a tension T, let's say, at one of the end of the rope. You're holding it from here. Let's say it's a 2-meter long rope. So what do you think? If you're applying a force T on one of the end, will the block feel the same force T, or it will feel a lesser force or a greater force? If you've connected a rope to a block, applied a force T on one end of the rope, how much force the block would feel? Same T force, more than T, less than T, or insufficient information is there? Okay, so lesser force, more force, same force. Okay, all options I can see here. People giving all different answers. Now, the actual answer for this is it cannot be commented right now. It's an insufficient information because you'll be surprised to know that block will be able to feel the same force T. The force, let's say, experienced by block is F. Let me call the force experienced by block as F. Now, F is only equal to T if the rope is massless. Then only this can happen. So the same force from the rope will reach the other end if it is massless. If rope is having a mass, then force will be lesser. F is lesser than T if rope has a mass. Now, obviously, imagining something massless is absurd. All the quantities around us are having some mass. They can't be massless. So in real life, no rope can apply the same force. It is always somewhat lesser than what you apply. Okay. So although the difference is not much in most of the cases, suppose you applied a 20 Newton of force. So it's just that some 18 Newton will reach. Hardly 2 Newton will be taken away. It all depends on how light the rope is. If rope is very light, then the decrement will not be much. If rope is very heavy, you're using a very heavy rope, then only a little amount of that will reach on the other side. Do you want to understand the reason behind this? Should we? Okay, so let's try to understand the reason why this is the case. Now, if rope has a mass, and I'm calling that there is a block of mass M being pulled, rope also has a mass. Why don't we consider it as a block also? So what I'm saying, if we have been given a block of, let's say, mass 20 kilograms, and then we have a thick rope which is pulling it, and let's say the rope is thick and that also has a mass of 5 kilograms, and then we are applying a force on it of, let's say, 40 newtons. This system of 20 and 5, we must analyze each of these masses individually. Let's see first of all what rope will be doing or what block will be doing. So block would say that I am feeling that rope has applied a force on me, some force F. That's why I start to move to the right. That's what block would say. And if we ask rope would say that obviously I'm feeling a force that you are applying, 40 Newton, but I'm also feeling a force that block is applying on me. Do you agree? When you pull somebody, you feel that pressure on your hand. Why? Because Newton's third law. Every action has equal and opposite reaction. If rope pulled the block with the force F, what the block would have done? Block would have applied equal and opposite force on the rope. Do you guys agree? This rope would have experienced the same force F backwards. I'm sorry, let me see where it has gone. Some rope pulled us up. We need to go down. Yeah, here it is. So I repeat again what we are doing. We are saying the rope pulled the block with a force. And so according to Newton's Third law, if rope pulled the block, block will pull the rope back with a force F. Everybody clear with this part? Every action has equal and opposite reaction. So if I ask you that now if they start to move, you start to drag the system. You're dragging the rope also, you're dragging the block also along with you. So do you agree if system is moving together, they will move with the same acceleration? Rope also moves with A acceleration, block also moves with A. So now we can write it here. Is moving with A, is moving with A. So now if we write the equations, which force is moving the 20 kilogram? F force is doing that. So we can just apply Newton's second law, F equals ma. So F is 20A. That's the first equation. And what about the rope? Rope too has a mass, 5 kilogram. What is the net force felt by the rope? It's like a tug of war. Someone pulling from the right, someone pulling from the left. So what is the net force on it? Net force on it will be 40 minus F. That's the effective force that it will feel, isn't it? No, it can't be zero. If it is zero, how will it accelerate? Isn't it? So net force is felt by the rope. And that net force is equal to ma, 5a. And so see, now we have two equations to be solved. Equation number 1, equation number 2. And if we solve, what do we get? Let's substitute from first equation the value of F. It's 20a. That's equal 5a. And that tells me that what is the value of A? A is 40 by 25, which is 8 by 5. That's the acceleration. And if acceleration is this, how much is the value of F? Force experienced by the block. 20 into 8 by 5, which is only 32 newtons. So that's what I told you. That if rope has a mass, then the force experienced by a block will be lesser. We applied 40 Newton, but how much block is feeling? Just 32. It's less. Samiksha is asking, can you explain why 40 minus F equal 5A? Samiksha, this is Newton's second law. I have written F equals ma. In that Newton's second law, that force is the net force. All right. It's always the net force. What is meant by net force? Just see the total effect. Because we could have had a condition where let's say two forces are acting equally, 5 and 5. Now, will you going to say that this block will move where force is 5 equals ma? Will you write that? No, right? What will you going to say? You will say that this block will be at rest. Why it is at rest? Even after force is acting on it. Because forces may be acting, but what about net force, net effect? So net effect is 0. Similarly, here we can't say that 40 newtons is acting on rope. There are two forces, even F is acting. So we must subtract the two and then show the net effect. Yeah, so now what Akhil is asking, where did the rest of 8 Newton went? So yes, that's a good question. Can you all answer? Block is only feeling 32 Newtons. Yes, so 8 Newton actually went in moving the rope, in accelerating the rope. All right. Sir, why 40 minus F not F minus 40. So Kishore, in a tug of war, who wins? Where the rope moves in a tug of war? Where there is a greater force, right? The team that applies more force, it moves towards that side, correct? So if rope is accelerating to the right, then who must be applying greater force, 40 Newton or F? 40 must be greater, right? So that's why we take 40 minus F, greater minus smaller. And you can check that also. You can check that F came out to be 32. It was lesser than 40. Sir, why F is replaced by 20A? So Jay and Jainil, that is because of the first equation. We substituted. This is what we got from the block. So I solved equation number 1 and 2. So sir, can we prefer less weight of the rope to be used to have greater force? Yes, Akhil. This proves that whenever you have to use a rope, just take a rope of lesser weight. But there is a problem. The moment we start taking a thinner rope, there is a possibility for it to break as well. So try to take a material where the weight is smaller, but the strength is huge. Things should not break. Strength is also an important factor. Sir, aren't there massless ropes? No, Jayesh. Massless ropes don't exist. Massless matter doesn't exist in universe. Everything has a mass except photons. Photons rest mass is 0. Light. So this rope will have mass, and hence the same force never reaches on the other side. Don't we need to simplify 8 divided by 5 per meter second square? No, we can just keep it like that. Sir, which will do vectors or calculus? First, we will do calculus, Sambhav. After doing calculus, we'll do vectors. Huh, Jayesh, in general, in theory, we will going to take it. You asked me, sir, don't the massless ropes exist? My answer is they don't exist. And not only my answer, that's a fact. But in questions, we do say that massless rope is there. And many people actually ridicule physics. They say physics has so many absurdity. It just assumes massless rope, it doesn't exist. It assumes no air resistance, when in real life there is air resistance everywhere. So ideally what physics says, if you drop a metallic ball or a light feather, both will fall at the same time, isn't it? But real life, do you see it happening? No. Real life, the feather comes down very slowly, while the metallic ball falls really fast. Why? Because there is air resistance. Air is there. Air doesn't allow the feather to fall down. But if you do the same experiment in vacuum, if you drop a metallic ball and feather in vacuum, you will see them going simultaneously. They will hit the ground at the same time. So people say, does physics assume things which are not there? No, no, no. Don't be in that fallacy. Physics doesn't assume. Right now, I solved the question with rope being there, rope also having mass. So we don't need to assume, we can solve it, but we just do it for your ease, for the ease of the students, that let's not give you the complexity of having a rope with mass. Otherwise, every time you would have to calculate the force first, then after that, see its effect on the block, and then do many other things. So better we give you massless for your ease. Similarly, it doesn't mean that we don't know about air resistance. We even know how the air resistance force acts. That's the whole aerodynamics physics. The aerodynamics force is given like this. If an object is going through air with speed v, air must be crossing it. and this must be applying some resistance on this object. Then we even know that air resistance drag force, the force that will be deaccelerating it. Its relation we have found out to be this C1V plus C2V squared. And you put a negative also to show it's always opposite to the direction of motion. Now here, what are C1 and C2? So C1, C2 are constants, which depends upon the shape of the object, which fluid we are talking about, whether we are moving through air, whether we are moving through water, whether we are moving through some other kind of gas. So all these constants depend upon C1, C2. No, Sambhav, this is not Bernoulli's principle. Siddharth, it's not like friction. In a way, it's friction, but very different from it. Friction doesn't depend upon velocity. This force depends upon velocity. So constant C1, C2 are dependent upon shape and size of the object. The outside air, what is its density, and so on. And that's why you must have seen in aerodynamics, it highly matter what is the shape of the car. So all the high speed cars, you will see they have nice curvy structure. All that curvy structure is to allow air to pass through. They, with their calculations from here, try to minimize the air resistance as much as possible. What is the difference between resistance and friction? Friction is, Jayesh, the force between two surfaces when they slide over each other. So it has two types also. Static friction, kinetic friction. Resistance simply means when object cuts through air, it feels a resistance. That's resistance. It doesn't have types. Well, friction is completely a different phenomena. When object is falling from a height, does gravity increases its speed? Yes, Nihal, that's very obvious. That's why the objects speed up when they fall down. So again, do you think that right now we should tell you to use this formula in every question? Because even this V will be changing. So a simple question when you will be taking an object is dropped and I ask you what is its acceleration, now you won't be able to say G. If I give you air resistance, then you would have to consider this force. Then you would have to calculate the values of C1, C2, substitute over here, and then find the acceleration from that. Things will gonna get very complicated. So it's only for the ease of student, we physicists give you simple cases that, okay, neglect air for the time being. Okay, have a maskless rope, easy for you. So there could be air resistance in water. No, Jayesh, it's called the resistance of fluids. Fluids involves everything, anything that can flow. Water is also fluid, air is also fluid. So this formula is also valid for water also. Okay. So in water, you won't call it air resistance. You will just call it water resistance. So the better term for this is drag force. When you cut through a fluid, it drags. So that's what we call it. All right. So from now on, you should remember this. That only if rope is massless, that you can do this. Okay, sorry, I didn't see that. Yes, you just write there could be resistance in water. Yes, you're right. Okay. All right then, guys. So that's it. Hoping to see you in the regular class. All the people also in the YouTube, you can come and join in the regular class on 10th May, and we'll be doing many interesting thing there. Okay. Okay, on YouTube, people are asking for notes. Notes you can get through contacting that link, askIITians JEE as it is written. There we're going to give you, okay? It's from 10th, Sayed, okay? 10th, you will going to get the mail regarding it. All right, goodbye, everyone.